Welcome to Maths with EJD. I'm still talking about systems of differential equations, and particularly I've been talking about things like stability, phase plane analysis. I've been talking about bifurcation, and then we mentioned chaos previously, but here we're focusing on how bifurcation and chaos come together. So it's a continuation of the previous video where we introduced ourselves to the concept of bifurcation, talking about bifurcation theory. So here we're talking about bifurcation and chaos. And here we want to see some advanced types of bifurcations, particularly those that lead to chaotic behavior. Because like we said, bifurcation is about change of uh, stability condition, you know. So like you can have a stable system becoming unstable as you vary some parameters and things like that. So here we are seeing advanced systems where things can lead to chaos. So let's start with that right away. So let's talk about advanced types of bifurcation. Okay. So first of all, we have what we call the period doubling bifurcation. So in the previous video, we had seen things like saddle node bifurcation. Uh we saw transcritical bifurcation. We saw what else did we see? We saw what's that now? Pitchfork bifurcation where we saw supercritical pitchfork and subcritical pitchfork bifurcation, and then we saw Hopf bifurcation. Interestingly, in this video, I'll be showing you what Hopf bifurcation looks like, the Van der Pol oscillator kind of thing. So here we talk about period doubling bifurcation. Period doubling bifurcation. So here, uh, this bifurcation, this bifurcation leads to a doubling, it leads to a doubling of the period of oscillation, doubling of the period of oscillation. Okay, so in that case, successive period doubling, successive period doubling, okay, can eventually lead to chaotic behavior. So it's more like it's a kind of chain reaction. One becomes two, two becomes four, four becomes eight, eight becomes 16, 16 becomes 32. And before you know it, the whole place is crowded, that kind of thing. So that's the idea of period doubling bifurcation. And we have an example still related to the idea of a logistic map. Okay. So in the logistic map, which is xn plus 1 equals, that's xn plus 1 equals rxn into 1 minus xn, right? So r increases, as r increases, the system undergoes successive period doubling. Successive period doubling, successive period doubling bifurcations, leading to chaos. Leading to chaos. Okay. So we're going to see that after now. Then that's number one, right? Talk about period doubling bifurcation. So we also have what we call the Neimark-Sacker, Neimark-Sacker, Neimark-Sacker bifurcation. So this occurs in discrete, dynamical systems. Causing discrete dynamical systems, leading to the creation, of limit cycles, or what we call centers, I believe, when a fixed point, becomes unstable. Okay, so an example. So in systems like the Hanon map, okay, that should be Hanon map or something like that. In systems like the Hanon map, the Neimark-Sacker bifurcation leads to periodic orbits after the parameter passes a critical threshold. Passes a critical threshold. Okay, we also have okay, that's so the example of that. Oh, okay, that's the example already. Yeah, okay, that's the example, sorry. Now we go for another one. This is the okay, so yeah, we've talked about two right here. Okay, two there. So let's talk about it. The third one for advanced bifurcation types, we have the collision bifurcation, border collision bifurcation. Okay. So here, this occurs in piecewise smooth systems, in piecewise smooth systems when the trajectory, we talked about trajectory the other time when we're looking at phase plane analysis, when the trajectory crosses the boundary between two regions, leading to a sudden change, in system behavior. Okay. An example of this would be a piecewise a piecewise a piecewise linear system a piecewise linear system can experience a border collision bifurcation where the system's attractor changes drastically. Okay, so that leads us to the idea of chaos. So let's talk about chaos and the Lorenz system. Chaos and the Lorenz system. Coming from that, right? I intended to do green. Yeah. Chaos and the Lorenz system. So we have chaotic behavior in the Lorenz system like that. But let's see what this is about, right? So chaos chaos refers chaos refers to the unpredictable behavior. Unpredictable behavior in a deterministic system. So unpredictable behavior is okay when you have a probabilistic system, all right? Something that is probabilistic, okay, or stochastic, right? Unpredictable behavior may happen there. But when you have a deterministic system where the input determines the outputs mostly, and it is now unpredictable, then that's chaos. Chaos refers to the unpredictable behavior in a deterministic system, okay, where small differences, small differences in initial conditions, small differences in initial conditions. Normally, right, initial conditions are not supposed to upset the system too much, but when you change the initial condition a bit and something big happens, then it's chaotic. So when small differences in initial conditions can lead to vastly different outcomes, vastly different outcomes. Okay. So this phenomenon is a hallmark, is a hallmark of sensitive, hallmark of dependence, sensitive dependence on initial conditions, sensitive dependence on initial conditions. So this is an important term, sensitive dependence on initial conditions. That's what happens here. Now let's talk about the Lorenz equation. So the Lorenz equations, the Lorenz equations are a classic example of chaotic behavior, of chaotic behavior. These equations describe convection in the atmosphere, convection in the atmosphere, and exhibit exhibit chaotic solutions, at at certain parameters, at certain parameter values, showing a a characteristic butterfly attractor. We have the butterfly attractor. So, and that's why we talk about the butterfly effect, that butterfly flaps its wing in one part of the world and then it causes something serious in another part of the world. Okay. So, the Lorenz equations, equations equations are expressed as the system of differential equations, which we are talking about, right? The system of differential equations, dx dt equals sigma into y minus x. Then you have dy dt equals x into rho minus z minus y, like this. And then you have dz dt, equals xy minus beta z. So everything put together is what you know as the Lorenz equations. Okay, these are the Lorenz equations. So as simple as this may seem, right? it gives rise to some very interesting chaotic behaviors, which we are going to see later, very soon. I mean, you know, in Python. So now let's talk about some real world examples of chaotic systems. Real world examples of chaotic systems so that a little change can lead to something serious. Chaotic systems. Okay. First of all, we have our weather systems. Okay. We have our weather systems. So weather is inherently chaotic with small changes in atmospheric conditions leading to vastly different weather patterns over time. This makes long-term weather forecasting challenging. So it's very difficult to forecast weather, right? So because it's quite chaotic in nature because I mean like where I live, for instance, you can predict that it's going to rain and then something seriously drastic happens. So of course, the system for prediction are being increased and they are being made more efficient. But even with that, you still have uh, weather systems very unreliable. Okay, and that's why you can't predict for more than maybe a couple of days at a time. Okay, then we also have population dynamics. So population dynamics can also be chaotic in nature. Okay. Population dynamics. So in ecology, systems like predator-prey models exhibit chaotic behavior, where small changes in environmental conditions or species populations can result in unpredictable population cycles. And number three, you have electrical circuits. Electrical circuits. So nonlinear circuits, such as the Chua circuits, there's something called the Chua. You have the Chua circuits. So nonlinear circuits, such as the Chua circuit, can exhibit chaotic oscillations. These circuits serve as practical examples of how chaos can emerge in physical systems. And then number four, you have stock markets, of course. Yeah, the stock market can be highly unpredictable. So economic systems, including stock markets, can exhibit chaotic behavior where small shifts in economic parameters like interest rates or consumer confidence can lead to large unpredictable market swings. Imagine just an election can lead to significant change on the stock market, right? So those are practical examples of chaotic systems. Now, to round off this video on chaos, let's look at some systems we've made mention of, how they go. So in the previous video, I talked about the Hopf bifurcation, whose example is the Van der Pol oscillator, and the equation is what you see there: dx dt equals y, and the y dt equals mu into 1 minus x squared y minus x. I mean, we can easily make that into a system of into a second order system because the x dt is y. So dy dt. So it means that dy dt is simply the same thing as the squared x dx, the squared x dt squared. So we just have x prime prime equals this side. So that's easily a second order thing. So so with the code, look at the code now. So we have defined that equation. Dx dt is y, dy dt is mu into 1 minus x squared times y minus x. And then we have initial conditions. So if x is 1 and y is 0, basically. And then, of course, we have this division now. So mu values, we take three different mu values, 1, 3, and 5. So we can vary that also to see what that looks like. So if you run this, we have what we call the Hopf bifurcation. So you can see how that goes. So it's depending on what value mu is, you have that Hopf bifurcation. Okay, to make things clearer, right? Just uh let's start with just one. Okay. So with one, see what this looks like. So you have that oscillation going that way. So it's oscillating for sure. And then imagine if we have 3.0. Okay. Okay, it's still, so you can see there's a bit more to that. And then we have 5 now. You have this. So, but then let's have the three together. If we have the three together, it's more appreciated. Okay. Yeah. So this now. So we have everything together. So when it's 1, you have it in blue. When it's 3, you have it in orange. And when it's green, you have it in green. So that's how Hopf bifurcation looks like. All right. Um, okay, in our previous lesson, let me see what we said about bifurcation in our previous lesson. I think that was about the last thing. So in a Hopf bifurcation, equilibrium becomes in a Hopf bifurcation, a stable equilibrium becomes unstable and gives rise to periodic behavior or limit cycle. So you see that thing is like a limit cycle because the shape, as you can see, though it's not a cycle, a circle per se, but it is elliptic, kind of elliptic in nature. So that's a limit cycle. Then for a logistic map, now of course we expect chaos as the values of R increase. So we define the map in line 6 where we talk say Rx into 1 minus x, right? And then the initial condition for x is just 0.5, so we can keep changing that to see what happens. And number of points to plot after transients, so last is 10 here. If you take 100 iterations and run this, we have we have okay, it takes a bit of time because we are doing 100 iterations. So if you want, so you can see you have some kind of doubling. So 1 becomes 2, 2 becomes 4, and before you know it, 4 becomes 8, and before you know it, like you have even lost count. So that's serious chaotic behavior. That's period doubling bifurcation using a logistic map. Okay, so if I increase the number of iterations now, it takes a bit more time. Okay, so if I make X 1, let's see what happens. Maybe it will not be that fast. Okay, it won't be that. So the doubling, we can still see it probably more clearly. So I'm doubling before we lose count. Okay, yeah, it's still pretty much about the same thing. So, it starts from X equals 0.1, and before you know it starts really escalated like that. Okay, so we have that. Then we have chaos in Lorenz system, which is a system for convection in the atmosphere. So that also is chaotic in nature. So we have the initial condition here to be 1, 0, 0, x is 1, y is 0, z is also 0. Then beta is 8 over 3, rho is 28, and sigma is 10. Now, these are parameters for Lorentz system to be chaotic, actually. So we can keep varying them, right? So, and with this, you see a lot of uh we can see oscillatory patterns and everything, but then it's before you know it, it becomes really chaotic and you can't even follow. And it looks like a butterfly, right? And that's the butterfly attractor kind of thing we're talking about in the teaching, right? So that's about bifurcation and chaos. All right. So, and we have chaotic things happening in our day-to-day system. So this brings us to the end, I can say, of the system of differential equations. So after now, still on that differential equations, I'll be talking about uh, Lap Laplace transforms. But I'm going to make it a standalone playlist, which I'm going to add to the differential equations playlist. And after that, we still have the partial differential equations to go. Probably we'll stop with partial differential equations because I'm not sure. Maybe after that, I don't think there's anything. Interestingly, I've already dealt with numerical analysis, of even ordinary and partial differential equations. So that will make sure we have completed everything we need to do with, differential equations by the time I'm done with Laplace transforms and partial differential equations, I think. So thank you so much for listening. If you let me know in the comment section how helpful these videos are for you. Let me know how helpful these videos are. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. And if you have not subscribed to the channel, please go ahead and subscribe. If you have subscribed, thank you so much. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Okay, you don't want to miss out on anything. So, like I said, in the next set of videos, I'll be talking about Laplace transforms, which is still talking about differential equations. Um, Laplace transforms helps to transform differential equations into algebra, which we can solve and then take it back, using inverse Laplace transforms. Okay. So let me also know if there's okay, yeah, I've said that already. Then like and share, right? Share these links, share the playlist and everything for people who need to get clarity on any aspect. I've done a whole lot in this channel already. This like we're approaching like 700 videos, and different topics, game theory, calculus, matrices, all kinds, different statistics, probability, very comprehensive, starting from the very beginning to very complicated ideas. All right, so be sure to share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.